What mysteries lie beyond the observable universe? Our observable universe spans 93 billion light-years, but that's probably only a fraction of what it is. From multiple theories to potential changes in the laws of physics, we'll explore key ideas that challenge our understanding of reality. Join us as we push the limits of cosmic knowledge and wonder what might be beyond our cosmic horizon. The observable universe is defined as the part of the universe that we can see or see from Earth, extending from the beginning of space to the farthest distances that light can travel. Because of the finite speed of light, which travels at 300,000 kilometers per second, we can observe regions of space long enough for us since the Big Bang. Currently, this distance is about 13.8 billion light-years, meaning that we can detect objects up to 13.8 billion years. This limitation is not only of distance, but also of the nature of space and time. As the universe expanded after the Big Bang, the maximum distance we could observe grew. But due to this rate of expansion, regions of space are moving away from us faster than the speed of light. Therefore, there will always be parts of the universe that light cannot reach, a phenomenon known as the cosmological horizon. The observable universe itself is only a fraction of what it is. Beyond this horizon lies space filled with galaxies, stars, and other cosmic phenomena that we have never seen before. These regions are theoretically part of the universe, but are inaccessible due to the limitations imposed by cosmic expansion. Understanding the observable universe helps bridge the gap between what we know and what is beyond our current understanding. The limitations remind us that there is still much to explore, pushing the boundaries of space knowledge into regions our instruments may never reach. Our understanding of the observable universe has evolved dramatically over the centuries, reflecting advances in technology, mathematics, and scientific theory. In ancient times, people viewed the cosmos through a geocentric lens, believing that the Earth was the center of all celestial movements. Observations were limited to the eye, and the universe appeared to be a vast expanse of stars. But this perspective changed with the work of astronomers such as Nicholas Copernicus, who proposed the heliocentric model, placing the Sun at the center and ultimately broadening our view of our place in space. The invention of the telescope in the 17th century was a turning point in astronomical observation. Galileo Galilei's use of this new technology revealed craters on the moons orbiting Jupiter, and the phases of Venus, shattering the concept of a perfect and unchanging sky. As telescopes improved, so did our ability to detect distant galaxies, which led to Edwin Hubble's discovery of the expanding universe in the early 20th century. This discovery changed our understanding of space, giving us a deeper appreciation of its vastness and the relationships between celestial bodies. Technological advances in modern times have allowed us to look at the universe even better. Satellites, such as the Hubble Space Telescope, and missions such as the Cosmic Background Explorer, have provided information on the cosmic microwave background radiation, essential to understanding the early universe. Through these observations, scientists developed the Big Bang theory, shaping our view of cosmic evolution from the initially hot and dense state to the vast and cold universe we observe today. This growing understanding reflects not only the dynamic nature of scientific inquiry, but also the impact new discoveries have on our understanding of the universe. Each advance in our observational capabilities continues to challenge and refine existing theories, revealing that the observable universe is more complex than previously imagined and inspiring further exploration of space beyond our current limits. Current estimates place the size of the observable universe at about 93 billion light-years in diameter. This measurement covers the great distances between the Big Bang and the Big Bang 13.8 billion years ago. However, due to the expansion of the universe, The regions that emit the light that allows us to observe them are now much farther away than when the light first appeared. The observable universe is not a static boundary. As the universe expands, our ability to see further into space increases, even though it is limited by the speed of light. So what we can observe right now is only a fraction of the entire universe. As new astronomical instruments and technologies are developed, our understanding of distances in space improves, allowing astronomers to refine these estimates. Interestingly, the observable universe represents only a small part of the universe, which could be much larger or infinite. Some theories suggest that there may be other regions of space beyond what we see, from which light has yet to reach us, hinting at space filled with unknown territories. These estimates continue to evolve as we gain a deeper understanding of cosmic expansion and improve our observational techniques. Each insight adds a layer to our knowledge and sparks curiosity about what lies beyond the boundaries of our observable universe. Measuring distances in the observable universe is a complex endeavor that uses a variety of techniques and methods, each adapted to different scales of cosmic distances. For nearby objects, astronomers often use a method called parallax, which involves tracking the Earth's orbit around the Sun against the backdrop of distant stars. By measuring this shift, scientists can calculate the distance to the star using simple geometry. This method is most effective for stars within a few hundred light-years from Earth. As distances increase, astronomers turn to specific candles, which are objects with a certain brightness, such as supernovae or variable stars called Cepheid variables. Astronomers can determine how distant these objects are by comparing their observed brightness with their intrinsic brightness. Supernovae, in particular, serve as powerful tools because they can be observed at great distances, measuring billions of light-years. At even greater distances, scientists use the redshift of light, which is the phenomenon that light's wavelengths stretch as it moves away from us. The farther away an object is, the faster it appears to be moving away due to the expansion of the universe. By analyzing the amount of redshift, astronomers can estimate distances based on the relationship between redshift and distance, governed by Hubble's law. This method is essential for mapping the large-scale structure of the universe and understanding its expansion. Combining these techniques provides a comprehensive framework for space travel. With advances in technology and observational capabilities, our ability to accurately measure these dimensions continues to improve, helping to better understand our universe and our place in it. Each new discovery allows us to take a closer look at space, revealing its vastness. The most distant objects we see in the universe are galaxies and gamma-ray bursts, some of which formed when the universe was part of the modern era, about 400 million years after the Big Bang. One of the best-known galaxies is GNZ11, observed at magnitude 11.1, about 13.4 billion light-years from Earth. This galaxy provides important information about the conditions of the early universe, allowing astronomers to study how galaxies formed and evolved. Another remarkable category includes gamma-ray bursts, which are extremely energetic bursts that can outshine entire galaxies. The most distant gamma-ray burst is GRB 2012-120A, observed at a redshift of around 15.2. This explosion occurred when the universe was about 500 million years old, giving scientists a wonderful opportunity to study phenomena from the time when the first stars and galaxies formed. In addition, the Hubble Space Telescope and other observational instruments have detected ancient massive galaxy clusters such as MAX J1149 and 5+2 expanding our view of the past. These clusters not only help astronomers study the early universe, but also help us understand cosmic evolution and the distribution of dark matter. These observations demonstrate the amazing capabilities of modern telescopes and advances in technology. Each discovery of distant objects allows researchers to piece together a timeline of the universe, providing valuable information about its formation and the processes that shape the cosmos we observe today. Beyond the cosmic horizon of our observable universe remains a great mystery. This region consists of regions of space from which light has not been able to reach us since the beginning of the universe. Although this limits our ability to observe, many scientists speculate about what might happen in these unseen regions. Beyond our observable universe, there may be galaxies, stars, and space structures similar to what we see, but we have no direct evidence of their existence. Theoretical models show that the universe is expanding infinitely beyond what we can observe. In this case, regions of space can be filled with skyscapes that reflect structures within the observable universe. This means that countless galaxies, with billions of stars and potential planets in each galaxy, may exist without our knowledge. This concept raises the question of the fundamental nature of space and whether other life forms could exist in this potentially infinite space. Additionally, some theories consider the possibility of multimedia, where our universe is one of many independent entities. Each universe may have different physical laws, stability, and structure. This concept is still speculative and a topic of debate among physicists, and it raises interesting questions about the nature of reality and our existence within space. The regions beyond the space horizon remind us of the limits of our understanding and the uncertainties that lie at the forefront of space exploration. With every advancement in technology and methodology, the desire to explore and understand these uncharted territories in space grows, driving the search for knowledge about what lies beyond what we can see. Outside of our observable universe, the nature of space can be distinguished in many interesting and fascinating ways. One possibility is that there may be different galaxies and star systems in regions beyond our understanding, some of which exhibit completely different structures or compositions compared to what we observe. For example, these regions may contain galaxies that formed under unique conditions that we do not yet understand, leading to a diversity of cosmic landscapes that include unusual formations or skyscapes. Additionally, there may be different physical laws or stable regions, especially if theories like the multiverse have any credibility. In a multiverse scenario, different universes may exhibit completely different conditions, including variations in fundamental forces, the speed of light, or the behavior of gravity. This can not only change the types of stars and galaxies that form, but also affect the basic building blocks of matter, giving rise to exotic particles or forms of energy unmatched in our observable universe. In addition, the distribution and behavior of dark matter and dark energy, the dominant composition of the universe, may be different in these invisible regions. Although we understand very well the effects of dark matter on observable galaxies, its nature and behavior may reveal unexpected surprises. Different concentrations or properties of dark matter may lead to unusual celestial bodies, or ultimately change the dynamics of cosmic expansion in these regions. Understanding how these regions differ from our observable universe can shed light on questions about the origin, evolution, and ultimate fate of what we know. Every new discovery in the observable universe reminds us of the limitations of our knowledge, sparking curiosity about what might await beyond the limits of our understanding. The potential for different cosmic realities sparks the imagination and fuels the drive for further exploration and discovery. Cosmic inflation is a theory that proposes a rapid, exponential expansion of the universe within the first fractions of a second in the moments after the Big Bang. This theory was developed to solve several puzzling questions about the homogeneity and isotropy of the observable universe. According to the inflationary model, the universe expanded at an astonishing rate, stretching from subatomic scales to macroscopic distances, eliminating disorder in its fabric. This inflationary phase is thought to have produced the relatively uniform distribution of matter and radiation we observe today. The meaning of cosmic inflation is beyond our observable universe. One of the main implications of this theory is that regions beyond the cosmic horizon may have undergone the same inflationary process, leading to convergence on large scales. Because inflation is so fast, large regions of space are beyond our ability to observe or detect, leading to a scenario where significant parts of the universe are inaccessible to us. This means that even if there were any changes in density or structure in those regions, they would be beyond our reach due to the finite speed of light. In addition, inflation introduces the concept of a potentially infinite universe. If inflation is not localized to our visible universe, but instead affects a larger space, this suggests the possibility of an infinitely vast cosmic landscape beyond what we can see. Each region likely underwent its own inflation process, creating separate pocket universes, sometimes called bubbles, each with different physical characteristics. If this is true, it could mean that other parts of the universe may have different fundamental constants, or even different physical laws. The concept of cosmic inflation raises profound questions about the structure and nature of the universe in general. It prompts us to explore things beyond our observable horizons and invites speculation about the properties of the realms that remain hidden. This framework encompasses not only our own universe, but also the potential diversity of reality beyond our observational capabilities. The concept of multiple universes originates from theories related to cosmic inflation and the multiverse. According to these ideas, our universe may be just one of many, each with different physical properties and laws. During the inflationary phase after the Big Bang, some regions of space could have stopped inflation while others continued to expand, resulting in bridges of space-time representing separate universes. These multiple universes may show major differences. For example, some may have physical constants that differ from those in our universe, leading to variations in the types of matter or forces present. Such diversity could lead to completely different galaxies, stars, and even potential life forms. This concept expands our understanding of reality to include things beyond our observable boundaries. Although the existence of multiple universes is theoretically possible, it remains speculative due to the lack of direct observational evidence. Many scientists are working on ways to gather data that lends credence to various theories. For example, the cosmic microwave background radiation may contain evidence of the inflationary period and collisions between our bulk universe and others. Traces of such space events may be detected by current or future observational technologies. The idea of multiple universes tantalizes the imagination and invites us to explore the fundamental questions of existence. Although we cannot directly observe these spheres, studying the implications of their existence complicates our understanding of the cosmos and prompts further investigation into the fabric of reality. Every multiverse theory mentions the great uncertainties that persist in our quest to understand the universe and our place in it. In regions beyond the cosmic horizon, the laws of physics may defy our understanding of the universe as we know it. If we consider the possibility of multiverses or regions, each universe may operate under its own physical laws and stability, different from those of our observable universe. For example, fundamental forces such as gravity or electromagnetism may have different strengths, leading to completely different behavior of matter and energy. One interesting scenario is the cosmological constant, which is associated with dark energy and affects the expansion of the universe. In other regions, this constant can take different values, potentially leading to higher rates of cosmic expansion. Such differences can also affect the formation and stability of structures such as galaxies and stars, creating environments that differ dramatically from our familiar cosmic landscape. Additionally, the basic particles that make up matter can take different forms or combine in unique ways, resulting in alternative substances and energy. Some areas may have entirely new forces or interactions, but must be observed in our universe. This can lead to exotic physical phenomena or conditions that defy our scientific theories, pushing the boundaries of understanding of modern physics. Although these concepts remain speculative, exploring potential differences in physical laws beyond the cosmic horizon sparks an imaginative inquiry into the nature of reality. They raise important questions about the limits of human knowledge and the fundamental structure of the cosmos. As scientists continue to probe the interior of our universe, the possibility that other regions operate according to different rules points to the quest to unlock the mysteries of life. The many worlds interpretation of quantum mechanics is a theoretical framework that states that every quantum event causes the universe to spread into many parallel realities. This explanation was first proposed by physicist Hugh Everett III in the mid-20th century. In conventional quantum mechanics, particles exist in superposition states, where they can exist in multiple states at the same time before being observed. The act of measurement seems to bring this superposition to a single conclusion. However, the many worlds interpretation implies that all possible outcomes actually occur, albeit in separate, non-communicating sectors of the universe. According to this explanation, every decision or random event creates a split in the fabric of reality, leading to multiple parallel universes. For example, if you flip a coin, you may see one universe land heads and another land tails. Each of these outcomes exists in a unique universe, meaning that all possible outcomes of quantum measurements coexist and are equally real. One of the most interesting aspects of the many worlds explanation is how to avoid the notion of wave function decay, a controversial topic in quantum mechanics. By removing the need for abstraction, the theory solves several philosophical and conceptual problems related to observation and measurement. Instead, reality is seen as a vast, complex structure of diffusion paths, where every decision and chance creates a new reality. The many worlds explanation remains one of several competing explanations for quantum behavior that has interesting implications for our understanding of reality and the nature of life. It challenges our preconceptions about determinism, free will, and the nature of time, and invites us to think deeply about the consequences of quantum events not only in our universe, but potentially in countless others. As scientists continue to explore the implications of quantum mechanics, the many worlds explanation is a bold and exciting possibility in theoretical physics. The concept of parallel universes is deeply connected to the multiverse theory, which holds that beyond our observable universe, there is a vast collection of universes, each with its own characteristics and laws. Although the term parallel universes often implies the existence of an alternate reality that is controlled by our own, the multiverse theory covers a wide range of possibilities, including different shapes and structures of the universe. In the context of multiverse theory, parallel universes can arise from multiple models. One popular approach is rooted in the many-world interpretation of quantum mechanics. Here, each quantum event leads to the creation of a new universe, showing all the possible consequences of that event. This means that for every decision made at the quantum level, a separate universe accounts for all potential paths, resulting in an interconnected web of parallel realities. Another aspect of the multiverse theory is related to cosmological models, especially cosmic inflation. In this scenario, our universe was one of many regions experiencing inflation. Each region can expand differently, leading to changes in fundamental physical laws, structures, or constants. These inflated regions can become their own separate universes within a larger multidimensional framework. In addition, some theories suggest categories such as line theory landscape, where a large array of vacuum states leads to many universes with different fundamental forces and particle types. Each universe can support a unique physical reality and allow for different configurations of time. Although each of these concepts represent different aspects of the multiverse theory, they all share the basic idea that our universe is not a single reality. Exploring parallel universes within a wide range of multimedia fuels the imaginative exploration of existence and enables a variety of experiences in different realms. It invites us to rethink the universe, reality, and even the nature of life within an infinitely complex cosmic realm. The theory of eternal inflation extends the traditional model of cosmic inflation, which describes the rapid expansion of the universe shortly after the Big Bang. Perpetual inflation assumes that the process of inflation does not end everywhere at the same time. Conversely, some regions of space may continue to inflate indefinitely, while others may stop inflation and become observable universes. Essentially, this ongoing inflation could create a scenario in which inflated regions continuously form, leading to a large and possibly infinite diversity. In this framework, the universe is viewed as a dynamic environment in which different regions can experience inflation at different rates. While parts of the universe cooled and settled, forming galaxies and stars, other regions remained in a constant state of inflation. Hence, new multiverses are constantly forming, each with different physical laws or constants. As a result, perpetual inflation supports the idea of multimedia filled with different realities that operate independently of each other. Eternal inflation further reinforces the multidimensional concept that our observable universe is just one tiny speck in the vast cosmic landscape. The implications of this theory suggest that environments in our universe may adopt completely different conditions, so that some may retain unique structures, fundamental forces, or even different dimensions of time and space. Additionally, the nature of eternal inflation suggests that this process is not a one-time event, but a dynamic system that continuously shapes the universe. This opens the door to the possibility of an ever-growing multiverse, where each bridge universe represents a snapshot of reality shaped by specific circumstances. Finally, the theory of eternal inflation combines the ideas of cosmic expansion and multidimensionality to provide a framework for understanding the vast complexity of the cosmos. It challenges our conventional view of the universe, invites us to consider the existence of unobserved realms that may operate according to completely different rules, thus enriching our understanding of reality. The landscape multiverse theory emerges from a theoretical framework that attempts to reconcile quantum mechanics and general relativity, suggesting that the fundamental particles of the universe are not point-like, but rather one-dimensional lines. Within line theory, the landscape concept represents a multitude of vacuum states, each corresponding to different configurations, physical constants, and forces. These vacuum states determine the properties of the resulting universe, leading to different realities. Compactness of additional dimensions plays an important role in line theory. Although our observable universe has 3 dimensions of space and 1 time, string theory suggests additional dimensions that are compact and unobservable. Landscape multimedia theory suggests that the configuration of these extra dimensions can produce an astronomical number of vacuum states. In fact, the estimates are based on 200 different probabilities in 10 different orders. Each of these configurations leads to stable physical laws and values that govern the behavior of matter and energy. As a result, landscape multimedia theory posits that our universe is one among a realm of potential universes, each of which emerges from different vacuum states within this landscape. Some universes may have conditions suitable for life, while others may lack the necessary structures or forces to support it. This means that the fundamental properties that we observe in our universe, such as gravity or the mass of particles, are not universal truths, but rather specific results as a result of the particular vacuum in which we are trapped. The implications of landscape diversity theory are profound, pushing the boundaries of our understanding of reality and living nature. This raises questions about the fine-tuning observed in our universe, since many physical properties seem to be precisely calibrated for the emergence of life. In this context, the multiverse provides a potential explanation. If there are many universes with different characteristics, then statistically, at least one universe like ours has the right conditions for life to flourish. Finally, multivariate landscape theory and string theory provide a rich and complex view of space. The universe we perceive is one of many unimaginable realities, each influenced by the basic structure and fundamental principle of the cosmos. Line theory. Finding evidence of other universes is a difficult challenge that sets the limits of our understanding of modern cosmology. One of the leading ideas comes from the theory of cosmic inflation, which suggests that our universe underwent an exponential expansion immediately after the Big Bang. This rapid expansion can lead to a multitude of spacetimes, each of which can form its own universe with different physical laws and constants. Although we cannot directly observe these other universes, we can look for clues in our own. One proposed method involves studying the cosmic microwave background radiation, the faint wake of the Big Bang. Scientists analyze this radiation for patterns that indicate anomalies or interactions with other universes. For example, if two universes collide, it can leave a unique signature in the cosmic microwave background that we can measure. Detecting such disorders requires highly sensitive instruments and accurate data interpretation, but advances in surveillance technology hold promise for the task. Another interesting avenue is the mathematical basis of string theory. This theory suggests that there are many dimensions beyond the four we experience. Some physicists suggest that these extra dimensions allow other universes to appear in our own. Experimental efforts, such as those carried out in particle accelerators, seek to reveal evidence of these extra dimensions, which, if discovered, could prove the existence of the multiverse.